Yes? Okay. Hello, welcome. My name is Kiedanski. I'm a PhD student under the supervision of Daniel Kaufman. I'm working on local energy markets, and today I'm going to be presenting a work which is under submission that we did with Ariel Orda when he was here last year. So, because I'm working in smart grids and most of people here are working on networks, I'm going to give a brief introduction of our motivations, and then I'm going to delve more into the problem. So basically, I'm going to give a brief introduction, an explanation of the problem we're trying to solve. I'm going to introduce some cooperative game theory that we're going to require, and then they're going to delve into the results. So as you can see from the title, we are dealing with storage, with games, and with RAM constraints. So basically, I'm going to start by explaining what I mean by that. First, why do I mean by storage? I'm not speaking about boxes. I might be speaking about flying wheels, or lithium batteries, or not containers, but maybe hydroelectric energy storage. Basically, we're trying to deal with ways of storing energy, but not all storage technologies can be used for the same purposes. And by this, I mean that we're mostly going to think about lithium batteries, like the Tesla Powerwall in what follows. So the next natural question is, why do we need storage? And storage has many purposes in the smart grid. The main one we can highlight are when we have renewable energy resources in the smart grid, sometimes it is hard to synchronize production with consumption. So by having storage in the grid, we can store the excess, the surplus of production, and use it whenever we need. Storage can also provide ancillary service to the grid, such as frequency regulation, voltage regulation, maybe phase switching. And it can also increase market liquidity when needed. So all these are very nice benefits that energy storage can provide in the smart grid. But the next question is, as a normal human being, why would I want a battery? And the answer to that is arbitrage. It's the ability to buy energy when it's cheap and sell it or use it when it's expensive. So I'm going to explain a little bit how this works. Last but not less important, why are we, our basic proposal in this work is that batteries are expensive, and therefore we are looking for ways to share the investment in them. Why do you mean they're expensive? The Powerwall 2 produced by Tesla is like the standard battery product in the market, and it's around $7,000. And sometimes the arbitrage gains that you can get are around €5 a month. So it's kind of hard to justify an investment in such a battery. Building hydro plants is not cheap either. And another source of batteries, which is getting increasingly popular, is the use of the electric vehicles batteries to provide all these services to the grid. But owners of electric vehicles might want to use their EVs to actually drive. And so scheduling the use of those batteries is a hard problem. And so we would like to have additional batteries in the grid. More importantly, think of the battery of an EV. The battery is in use while the car is driving, but most of the time it's idle. And so this idea that we have resources that are underutilized kind of yields this idea of sharing a resource. So I'm going to describe a little bit how arbitrage works, and then I'm going to dive into the game theory part. So this is kind of messy, but I'm going to explain. Imagine that the black curve is the consumption profile of a given user. This is in power. From this point, which says Tm to the right is the expensive period, and to the left is the cheap period. So what can we do with a battery? Well, basically, with a battery, we would like to shift all this consumption to this period, charge our battery this amount, and then just discharge it here. What happens? Batteries have a ramp constraint. That is, how much power they can supply in a given moment in time, which is this delta here. So this means that although I would like to shift all this energy to the cheap period, my battery cannot supply more power than this. So what is the red area here, I'm going to have to pay the expensive no matter what. What happens with the yellow area, the area that I might shift to the cheap period? Well, that area is mapped to the green one with diagonals here. And the purple one is the actual size of the battery. So in the end, how much energy will I be able to shift to the cheap period is going to be the minimum of the battery capacity, the green area, and what I actually have to consume. How can we write this a bit more formally? If I'm consumer I and B is a battery in general, the cost per day that I would have is the cost of the battery, the amount of energy I'm consuming the cheap period times the cheap price, the amount of energy in the expensive period times the expensive price, minus the difference of the amount of energy that I'm shifting. So how much energy I'm shifting? I'm shifting the minimum of my consumption under ramp constraint in the expensive period, so this area here. What actually the battery can discharge and the battery capacity. So this model ends up to be quite hard to work on, and there are a lot of things we can actually instantiate there. So we're going to work with some assumptions. First, we're going to assume that I think it's easy with the drawing. We're going to assume that these both periods are equal and that the battery can charge or discharge the same in both periods. That changes a couple of constants, not the quality of the results, but it makes the math easier. We are going to normalize time just to be able to speak of things between 0 and 1. And we are going to assume that energy consumption in the early period is 0. So and now to the important assumptions, if you want. We're going to assume that the cost of the battery is linear in the capacity. That means if I buy a battery with twice the capacity, I'm going to pay twice the price. We are going to assume that the consumption of energy is piecewise constant, but because data sets are actually sampled every discrete times, this is not actually a restriction. We are going to assume that the ramp of the battery, that means how much power they can provide, also grows linearly with the capacity. And finally, we are going to assume that the gap here between the expensive price and the cheap price is greater than the amortized cost of the battery per day. Without this, we can prove that the optimal action is not to buy a battery, so this is the only alternative we have. So under all this, what's left is, most of the time I'm not going to be talking about just one consumer. I'm going to be talking about a subset of them. So if I have a subset of consumers S, then their consumption is going to be just the sum of the consumption of each of them. And I can rewrite the cost of these consumers as this, where I drop some of the things along the way. I instantiated the cost as linear and the ramp constraint as linear. And again, this is in general for every battery. As a group of consumers, we're looking for the cheapest battery or the battery that optimizes our costs. So we're going to denote J of S, the actual cost incurred by this group of S consumers when they buy the optimal battery. And this is just minimization in one variable, the capacity. So this is basically the thing we have. This is our reality. So I'm going to detour a little bit into cooperative game theory, explain some concepts there, enough so that we can go back to a problem and try to solve it. Okay, so what's the main idea of cooperative game theory? I assume that most of you are familiar with game theory, traditional, but maybe not cooperative that much. So I'm going to explain. If I bore you, please let me know. Basically, the idea in cooperative game theory is that we have coalitions, such as this group S of players. Every coalition can find their cost or the value, depending of if we are spin out getting value or like reducing costs. This would be the costs of the coalitions we are considering. And what happens afterwards is that players have to decide how to split the profit or the cost of their coalition. And something important is that when we mean cooperative, we don't mean altruistic. Players are still trying to maximize their profit or minimize their cost, and they're not just willing to give everything to someone else.
Just to understand
yes.
The game part of the game,
yes.
This is because users share their battery and then their benefits? What is the idea behind it? What is the motivation? Why is there a coalition?
Yes, so basically if this, instead of being the profile of consumption of one player, is the profile of an aggregation of players, then we're going to find a battery that fits better this new profile. And we have to decide who gets to pay for the battery. So maybe this peak here is the fault of just one consumer that forced everyone to buy a bigger battery to be able to cope with that. And so we might be willing to say, because of your consumption profile is the one that cost us more, we want you to pay more for the battery because we think it's your fault.
But the battery is something which lasts over time.
Yes.
The profile is very sporadic.
Yes, we are assuming here that the consumption profile is the same for every day, and that a battery lasts 10 years. So we are looking at actually at the cost of the battery provided per day. We are here. So the main question we are trying to ask here is, will the grand coalition form? The grand coalition is the biggest coalition, the coalition of all players. And the reason it might not form is because maybe when we are all together, I propose a distribution of the cost of the profit. And some of you say, oh, no, I don't like that because if that's the proposal, I'd rather leave. And so this won't form. This is not stable. So the big question is this stable? Can we assume that all players are going to get together and cooperate, or that won't happen? So let's give a simple example to motivate this, and we are going to get back to this afterwards. Imagine we have a population of n players. X of them produce left gloves. N minus X produce right gloves. Neither of them can sell their glove alone. They sell by 0, but if they get one left and one right together, they can sell it for 1. So if we look at a group of S producers, where it's a mix of left producers and right producers, then the value they can get together is the minimum of left producer or right producers. Basically, if we have 10 users that produce left gloves and 2,000 that produce right gloves, the value they cannot get together is just 5. Because that's the amount of pairs they can sell. So this is a game. In cooperative game theory, when we have the characteristic cost or value function, which is this, that specifies how much a coalition gets, that's enough to say we have a game. So the question afterwards is, how do we solve this game? What do you mean by solving this game? So to solve a game is to find a payoff vector that specifies how much each player should pay or gets if we are speaking about profit. And we are looking for some nice properties about this payoff allocation. Basically, that is efficient. So when I use bracket notations, I mean the set from 1 to n. So this is the set of all players, the grand coalition. So that the sum of all of them equals the grand coalition. That if this is the cost, that players don't have to pay more than what they can get alone. Otherwise, they're going to leave and don't join a coalition. And if there's a group of them, that the group together doesn't incur more costs being together than what they can get alone. That's the basic idea. So this is going to get a little bit confusing. So I'm going to talk about cost games and value games. Cost games are games where you try to minimize your cost. Value games are games where you try to maximize your value. And depending on which we are dealing with, this is going to shift. So this is for cost games, but if we're talking about value games, this is the other way around. Basically, you want to get more value than what you can get alone. You want to get more value than what you can get alone. This is what. When I say an imputation, I just mean this to hold. So the main notion in cooperative game theory, I would like to say, is the notion of the core. I would say that is what is equivalent to a Nash equilibrium-ish. So the set is the set of payoff that satisfy these three properties. It's always defined, but it might be empty. It's defined by a set of linear inequalities. It's convex, it's closed. It's NP complete to decide whether it's empty or not in general. So it's kind of a hard problem. It can be unfair. We're going to talk fairness in a moment. And I haven't defined what domination is, but it's the set of imputations which are not dominated. So that's like a sense of stability, if you want. So back to our game, or to a small example. Imagine we have one left shoe producer and two right shoe producers. If we try to find out what the core of this game is, we are going to write the set of equations, basically, that every player should get at least his value, that a group of players should get at least what they get together, and that is efficient, which is what we have here. And so what happens if we try to pay epsilon to our right shoe producer? Basically, this gets transformed into this, and these two are a contradiction. Therefore, in these kind of games, the core automatically pays 0 to all the producers which are in excess, let's say, and pays all the profit to the scarce commodity. Yes, or? So if I have like 5 left gloves producers or shoes producers and 1,000, 1 million right shoe producers, the 1 million right shoe producers are going to get 0 because they are the surplus commodity, and the other ones are going to get all the profits, which I would say it's unfair. But because I'm not the only one that thinks this is unfair, there are other proposals of solutions of these kind of games. One of these is the Shapley value, which is basically a definition of just one single payoff. The Shapley value satisfies many nice properties. It's argued to be a fair solution. It might not be in the core, so it might not be stable, which is one of the drawbacks. And it's even used outside of game theory to do machine learning. The last solution I want to discuss with you before getting to our back to our problem, it's the notion of domination. We say that an imputation X dominates another imputation Y, and we write it like X dominates Y. If, and this gets a bit tricky, there's a subset of players which do better in X than in Y, which is this here, and their proposal of what they want to get in X is no more than what they can produce. Basically, if the current proposal is Y, and we get together with a set of S players, and we say we want X, for that to actually dominate and be an improvement over the current solution, we all have to get better, but we cannot ask more than what we can actually produce ourselves. That's currently the definition. So in this sense, we can define stable sets in the von Neumann-Morgenstern sense. If in this set there are no two pairs that dominate one another, and for each imputation outside the sets, I can always find an imputation in the set which dominates it. So I'm going to give you an example of this afterwards, so just keep it somewhere in the back of the head, and we're going to get back to that. So what we are trying to answer is whether the ground coalition will form, which is equivalent to asking 100% agreement between, let's say, neighbors of an apartment. So when are we going to use this kind of solution? If, for instance, we have to decide whether to buy a battery in an apartment, and our contract says that we all have to agree for such kind of modifications, then this understanding whether the ground coalition will form or not will help us understand whether there's a viable outcome of such situation. The case without ramp constraints and linear costs was solved before. Actually, that's our inspiration to work in this problem. And it was shown that the core is not empty. So there's always a payoff which is in the core, which is stable. With non-linear ramp constraints, the core might be empty. This is one of the things we proved in this work. With two players, linear ramp constraints, and we can show that the core is not empty. We just have a conjecture for the general case. Without ramp constraints, there is no benefit in collaboration, which is important. Basically, if we don't model the ramp constraints, it's always the same to buy the battery on your own or get together with someone to buy a battery. And we have a couple of general games we study, but I'm going to show you an example here of one of those families. Bear with me a second, and I'm going to try to skip this fairly quickly. Remember that we are trying to minimize this function. This function is convex, and basically it's a minimization in the reals. And the capacity of the battery goes from 0 to positive reals. So we are interested in finding out the derivative of this thing. The derivative, this term is constant in the capacity of the battery, so it doesn't matter. So here the derivative is P minus P, P, and the derivative of this thing. So basically what we try to understand here is how do we find the derivative of this thing, which is this thing, which is this thing. And so the problem here is that we have the capacity somewhere there in the middle, but it gets a little bit annoying to do all the math with that. So we find a way to change coordinates and make things easier. So if we look at this plot here, this is the consumption profile. This is the RAM constraint. And so this is the amount of this